Hi, I'm John. I'm a chemistry graduate student at UCLA, and now in this video we're going to be going over some chemistry topics. Hope you find this useful, and good luck in your course.
In this lesson, we're going to be looking at mass spectrometry. This is spectrometry, not spectroscopy. So the outline of this lesson is to basically talk about the mass spectrometer, the instrument itself, and then different features that you'll see in the spectrum, in the data that you output from the instrument, how to interpret that spectra, and then basically go over a summary. So this should be a bit shorter. It's more easy to interpret than IR spectroscopy or NMR spectroscopy. And so usually when you're solving these problems that you'll see in a separate video, you want to tackle the mass spec data first. So let's go ahead and move on into that. So mass spectrometry is an analytical technique for measuring the mass to charge ratio, or M/Z, of ions. Usually it's positive ions, and especially conventionally it was originally positive ions, but now both positive and negative can be measured. It's the most valuable analytical tool for determination of accurate molecular masses. And you can get extensive information about the molecular formula and structure of a compound from its analysis of this mass spectrum. It's also being increasingly important in biochemistry as well. So sequencing of proteins using this technique alone allows protein structures to be determined on virtually a single cell scale. Now, the instrument itself, the mass spectrometer, is designed to do three things. Number one, convert neutral atoms or molecules into a beam of positive or negative ions, usually positive. It separates the ions on the basis of their mass to charge ratio, and it measures the relative abundance of each type of ion. So from this info, you can determine both the molecular mass and the molecular formula of an unknown compound. In addition, you can obtain valuable clues about the molecular structure of that compound. So there are many types of mass spectrometers, but we'll basically just go over the instrumentation for one here. So this is a schematic diagram of an electron ionization mass spectrometer. But basically, samples of gases and volatile liquids can be introduced directly into the ionization chamber. Because the interior of a mass spec is kept at a high vacuum, volatile liquids and even some solids are vaporized. For less volatile liquids and solids, the sample may be placed on the tip of a heated probe that is then inserted directly into the ionization chamber. Now, another extremely useful method for introducing a sample into an ionization chamber is to couple this or link a gas chromatograph or a liquid chromatograph directly to the mass spec. So typically you might see GCMS or LCMS. These instruments can separate complex mixtures of molecules into pure fractions, and then each fraction is eluted from the chromatograph into the ionization chamber of the mass spec. So the vaporized sample in the evacuated ionization chamber is bombarded with high energy electrons that cause electrons to be stripped away from the molecules of the sample, giving positively charged ions. So the positively charged ions then are accelerated by a series of negatively charged accelerator plates into an analyzing chamber inside a magnetic field or an electric field in some spectrometers that's perpendicular to the direction of the ion beam. So these fields cause the ion beam to curve. The radius of curvature of each ion depends on the charge of the ion and its mass, as well as the accelerating voltage and strength of the field. The fragments or the charged pieces of the molecules then pass into a detector and to the mass analyzer. And so a mass spectrum is then generated, which is a plot of the relative ion abundance versus the M/Z ratio. So once the samples are in the ionization chamber, molecules are bombarded with a stream of high energy electrons, usually emitted from a hot filament, and then they're accelerated by electric field to energies approximately 70 electron volts. The collisions between molecules of the sample and these high energy electrons end up resulting in the loss of electrons from the sample, and that's how they form the positive ions, like shown here. So a molecular ion is the species that's formed by removal of a single electron from the molecule. The molecular ion belongs to a class of ions called radical cations. So here we have methane that's bombarded with the high energy electrons, and when an electron is dislodged from it, it gives a molecular ion with an m/z of 16. Now, which ion is lost in forming the molecular ion is determined by the ionization potential, or IP, of the atom or molecule. Ionization potentials, again, it's the minimum energy required to remove an electron from an atom or a molecule to a distance where there's no electrostatic interaction between that ion and the electron. So it's completely separated. Most organic molecules have these values between about 8 and 15 electron volts. But for our purposes specifically, it usually doesn't matter which electron is lost. In general, the radical cation is delocalized throughout the molecule. So because it's delocalized, you can write the molecular formula of the parent molecule in brackets with a plus sign to show that it's a cation, and with a dot to show that it has an odd number of electrons. So for example, here we have ethyl isopropyl ether. On the left-hand side, it's shown in that convention. But sometimes you might find it more useful to depict the radical cation that's localized at a certain position to better understand its reactions. And so that would be like on the formula on the bottom right-hand side. Now, the molecular ion can undergo fragmentation to form a variety of smaller cations as well as radicals in smaller molecules. However, you have to remember that only charged fragments are detected. Now, I have shown here an example mass spectrum of the molecule dopamine. So as I mentioned, you have plotted the relative abundance as a function of your ratio of mass to charge, m/z. The peak that results from the most abundant cation is called the base peak. And it's assigned an arbitrary intensity of 100. And the relative abundances of all the other cations in the mass spectrum are reported as percentages of that base peak. You can see also that we have given that the molecular weight of this dopamine molecule is 153. So you have labeled the base peak and a molecular ion peak. So the molecular ion peak has an m/z ratio of 153. So that peak is attributed to this ionized species, the radical cation. Sometimes you will see that the molecular ion peak is the same as the base peak, but as you can see, for example, here, that doesn't necessarily have to be the case. The base peak just corresponds to the molecular fragment that is usually the most stable. And I'll go into a bit more detail about that a little bit later.